from outside that frequently to take the same topics separately for 4 separate MSc courses. This is the one basic reason. And secondly, that having all students together also creates an environment of interactive sessions. All these lectures, please remember, whether by me or by any other experts from industry or research organizations, will have to be necessarily interactive in nature. So the first thing, all of you please remember that don't be afraid of asking questions. Just remove that inhibition from your mind totally in our classes, that somebody will ridicule you if you ask a question. There is nothing like a stupid question. A question is a question, a query in your mind. And if you do not ask questions, then all these unanswered queries remain accumulated in your part of the brain. And then subsequently, that gets saturated now without any answers. So please feel free. That is one thing. Now I have followed a practice of distributing small chocolates in the class to those students who ask good questions and or who give good answers to my questions. So even if one person wins 10 chocolates in a lecture, I don't mind, but I don't want that way. I want 10 students to claim 10 chocolates. Now there is a group of about 95, 96 students, and therefore you may be thinking, what if everyone gives a good answer or asks good question? Well, I will assure you, everyone will get a chocolate. Because chocolate is just an incentive. So don't hesitate to ask questions, right? Anytime you can interrupt me if a point is not clear. Similarly, the lectures of spectroscopy, which will be taken by Dr. Datta, a very renowned person in industry and an excellent teacher, please don't hesitate to ask questions. For that matter, as a standing instruction, don't hesitate to ask anybody any question. That is. Now, why is that separation has taken place? What has made these two solutes get separated? Difference in solubility, absolutely right. So we have taken advantage of the fact that at room temperature, sand is almost insoluble in water, whereas salt is freely soluble in water. So taking advantage of differences in the solubility of sand and salt in a given solvent, here it is water, we have been able to separate mixture of two solid solutes. Just another example where we have sand and another solute. Or let us forget about the sand. We have two solid solutes. One is completely soluble in water like sodium chloride, and the other solute is partially soluble in water. Let us say 1% of that is soluble. Now is the situation same as in the first case? Absolutely no. So in this case, when you take this mixture in a beaker, add sufficient quantity of water, stir it, all sodium chloride will dissolve. But alongside 1% of the second solute also will dissolve in water, and the filtrate will contain sodium chloride plus 1% of that. So is it a clear-cut solute separation? Answer is no. Then what do? You evaporate water and again add sufficient quantity of fresh water. Stir it. This time 1% of the 1% will go in the filtrate. Still in the second stage, separation is not complete. So the third step, and the fourth one, and the fifth one maybe. So we have to resort to a series of such dissolution, filtration, evaporation of the filtrate, again dissolution. So this process in the second example is known as fractional crystallization. Now in our first example, the separation of two solutes was complete in just one single stage. Whereas in fractional crystallization, the second example, it took us long time, repeated experiments, and therefore the process was not only lengthy, but the process was also laborious in nature. Right? So let us see that in the picture. And what I have done in preparing these slides over the years is I asked myself number of questions, and I went on answering these questions and modifying these presentations over the years. Next, please. This is a slideshow. Now here I have shown you the exactly same thing, that we have separation of sand and water. Don't take down, because these presentations will be available in the library on our common computer, right, in each department, where you can copy them subsequently, or you may use it in the library itself. So this is a very simple thing. You have mixture, beaker with water, glass rod is essential for stirring, then filter paper is there, funnel, and water bath at higher temperature, 100 degrees. Next. So you take this mixture, stir it. Next. Next. So you have sand undissolved. You filter. Next. Filter paper contains sand. You evaporate water from the beaker, and then sodium chloride remains in the beaker. Instead of solid solutes, let us have a mixture of two liquid solutes. Hexane, for example. Hexane, its boiling point is 60 degrees, and diethyl ether 37 degrees. So big difference in the boiling points of diethyl ether and hexane. So we take this in a round bottom flask, keep it on water bath at, let us say, 40 degrees to begin with, attach a condenser, and through the condenser, because diethyl ether is a very low boiling solvent, we circulate chilled water. And what will evaporate first? the ethyl ether through the condenser, it will get condensed, and then what remains in the round bottom flask is hexane. A single step separation of mixture of two liquids. The separation is on the basis of differences in the boiling points of two liquids. And this difference in the boiling points is very large, 37, 60. But we are not always lucky in practice to have such mixtures of liquids or solids having drastically different properties. So we have now in the second example a liquid having boiling point of 60, hexane again, and something other hydrocarbon with 65 degrees. Right? So the temperature difference is narrowed down. What it actually means is that at the boiling point of hexane 60, the other solvent will have also sufficient vapor pressure, and therefore when you distill off or try to distill off hexane by keeping the round bottom flask at 60, alongside hexane, a part of the second liquid also will get distilled off. Naturally, it's not a clear-cut separation. If it is not a clear-cut separation, we have to repeat the process again and again and again, like fractional crystallization. So in this process, this is known as fractional distillation. So one thing is common, that fractional crystallization and fractional distillation processes of separation are lengthy and laborious processes. Clear? Okay. Now I will take you, how many of you know Marathi by the way? So I can read you of Marathi sometimes. You try to understand through your friends. Subject and not positive, this is some example. Okay. How many of you are botanists? How many of you have studied botany during any one of these years? Okay. Not very many. I will take you back to year 1903. Almost more than a century ago. But very interesting thing happened. There was a Russian botanist, and the botanist had a peculiar problem with him. Scientific problem, not his personal problem. That he was trying to find out whether the green plant pigment, chlorophyll, is a single solute or whether it is a mixture of solutes. Because some people believed that it's a single solute, whereas some other group of researchers say, no, it cannot be a single solute, it is a mixture of solutes. And therefore the problem had to be resolved. So what Mikhail Sveit did, that he took a glass column, quite wide glass column of maybe 2 to 3 meters height. He put cotton plug at the bottom of that glass column with a tap attached at the other end of the column. We'll see that. And in a beaker, he took the powder of calcium carbonate, chalk, and made a slurry of that powder in a solvent, and he used a mixture of hydrocarbons of different boiling points. So when the slurry was made, he put the slurry onto the top of the column, inside the column on the top of cotton plug, and filled it up to a particular height. And then put cotton plug again on the top. Fine, this is one side of his experimental design. Then, in another small beaker, he took a concentrated solution of chlorophyll in the same solver. About 10 ml of that he put on the top of the column, which was filled with the slurry of calcium carbonate. Opened the tap, and when almost all solution of chlorophyll had moved down, he put ethyl alcohol on the top of the column and continued to wash the column for a number of hours. Clear? A glass column, cotton plug, slurry of calcium carbonate in petroleum ether, as it is called, a mixture of hydrocarbons. But whenever you say petroleum ether, you have to mention what is the range of hydrocarbons present in that. So petroleum ether can be 30-40 or 40-60, 60-80, 80-100, 100-122. Here he used 60-80. Quite sufficiently high boiling point. So, slurry filled in this, cotton plug again on the top, concentrated solution of chlorophyll put on the top, tap open. When almost all solution came down, continued washing the column with ethyl alcohol. And what did he observe after few hours? After few hours, he observed that on the white background of calcium carbonate slurry, beautiful colored bands were developed. Colors ranging from faint yellow to dark green. He isolated each band and characterized each band separately and proved beyond any doubt that chlorophyll is not a single solute, but it's a mixture of 5 solutes. And the problem of composition of chlorophyll was dissolved. And that was his main aim of the experiment. Let us see in the next slides. This was our next experiment. The biggest mistake, and I have done it purposely, the biggest mistake is round bottom flask is kept on a Bunsen burner. When you are dealing with organic inflammable solvents, you never ever do that. It's put on hot water bath, right? And therefore, this was the situation. Next, as I said, Mikhail Sveit's history. He was Russian botanist. Next. And his interest was, as I said, composition of chlorophyll. Then there were 2 schools of thought. One thought that it's a single solute, and the second school of thought that it's the mixture. And therefore this was to be resolved. So he had a beautiful experimental setup, and he conducted this experiment as I have described. We go quickly now through. Yes, this is the experimental setup, which you can see: slurry of calcium carbonate, cotton plug in the bottom, at the top, washing with ethyl alcohol. After concentrated solution of chlorophyll, went down the column. Next. Yes. obtained, hold on for some time, just click once, one more. Yeah. This is how he obtained 5 colored bands. He separated them, characterized them. Go ahead. What were these 5 solutes that he separated from chlorophyll? They were from top beta chlorophyll, alpha chlorophyll, xanthophyll, viola xanthine and carotene. All known solutes by chemist and botanist in 1903 also. Next. So each band was separated and characterized, and therefore a conclusion was reached without any doubt that chlorophyll is a mixture of 5 solutes. Okay, next. Look at the structures. Now why I have drawn these structures and shown to you? Because you must realize that each of these 5 solutes is a large molecule, big molecule, complex molecule. This is alpha and beta chlorophyll differing just by a methyl group. So the molecular weight is almost equal. Next. This is xanthophyll, also a large molecule. Next. Viola xanthine, xanthophyll and carotene. Next. And therefore, we must now appreciate the fact that, no, go back. We must appreciate the fact that as compared to fractional crystallization and fractional distillation, this process of separation is so easy, so simple and so time saving. Labels are minimum because you go on pouring ethyl alcohol on the top of the column and just watch whether something comes out. If it is colorful, fine. If it is not colorful, you are not that lucky as methyl white. Now, alongside proving that chlorophyll is a mixture of 5 solutes, accidentally Mikhail Sweet has discovered a method of separation. Is it not? That was not his aim, but serendipity, as it is called, accidental discoveries, were few in a few, but then it happened. So a new, simple, less laborious, time-saving method of separation was discovered by Mikhail Sweet. Now you have to do the naming ceremony. What do I call this new method? Fractional distillation? No. Fractional crystallization? No. He coined the term chromatography. Let us see, what does it mean? He visualized these 5 colored bands as if they were colored writings on the white background of calcium carbonate solution. And therefore, he termed chromatus means color, graphy means writing, chromatography. This was the term coined by this for this new method of separation. And just hold on. And then he published his work. In 1906, he published his paper and said that this is this and this is the method of separation called chromatography. Now you will wonder that because his bands were colored, he called chromatography. Now what if your solutes do not show any color? What's your name? Geetanjali. Geetanjali name was given by her parents or maybe grandparents. right? Have you changed the name? You have grown up so much and name is changed. Why? In the honor of the grandparents and parents, name is retained. So whether solutes are colored or colorless, if you are making use of that technique used by Mikhail Sveig, the discoverer, you will still call it a murder. Is it not? Okay. So let us remember one thing. In the field of research, when you publish your discovery or your findings the first time, the credit always is given to you if you publish it first. Now you know the British people, or for that matter, many Indians also, are cheaters. So side by side, a British chemist was working in England on similar problems, DT day. And he also separated solutes. But he did not publish his work before Mikhail Sveig published. But still in older British books, English books, they give credit to DT day. It's cheating, isn't it? But we must remember the father of discovery of chromatographic separation is Mikhail Sveig, not anybody else. Now when you discover something, there are two different ways now this young generation can do. During our time, we used to publish papers, finish, to get the credit, because we were not aware of what is meant by patenting. But now patenting and IPR issues have become a part of your syllabus or training, add-on training. So you have two alternatives. You can publish and get credit in the scientific community, or you can patent it and have that as your intellectual property. Just like you have your own house, your own scooter, your own car, that's your own property because you bought it. So also, if you patent your findings, then that becomes, and if patent is granted to you, that becomes your intellectual property. Now the question is, can you patent each and everything that you find out? The answer is no, big no. Unless your findings, unless your discovery has some novelty, you cannot patent. You may file patent, it will be rejected. So please remember, anything novel is patentable. Which is not novel is not patentable. I'll give you the best example. If you have read 5-10 years ago of Dr. R.A. Mashelkar, who was the Director General of CSIR Laboratories, Delhi. He fought for two patents which were filed in the US. One was on neem, the other one on basmati rice. And after fighting, he proved that they were not the original discoveries of those people who had patented it. So the patents were cancelled. So you may cheat the patenting agency also, but not for a long time. Because now, once you are patented something, it becomes in the public domain. You can access, she can access, anybody can access. And if I have an objection, then I can raise this objection in the court of law. Even prior to that, there is called as a provisional patent. So when provisional patent is filed, it goes in the public domain, and you come to know what he is doing or he is trying to patent, and you can take objection at that stage also. So you have two choices, publishing versus patenting. The choice is yours. If you patent, you cannot publish. If you publish, that published work you cannot patent. Right. Next one. It is very important. Recently, in 2006-7, I have been to United States for leisure trip. Next. And I had an opportunity to interact with the first year students in one of the universities in Cleveland. First year students. And many of them were talking about patenting, their findings. So patenting culture is right from the school days, in fact, in the Western countries. And in our country, unfortunately, this is lacking even among the PhD students and PhD teachers like me. And therefore, we have introduced this in our syllabus. Right, keep it. Now, I am a chemist. Many of you have done chemistry up to second year at least. So I have two questions to ask myself on Mikhail Sweig's experiment. And now your participation starts. Right. Now you have seen that beta chlorophyll, carotene. Carotene is the first to come out, followed by something, last is beta chlorophyll. Now my question is, why is that sequence? Under those experimental conditions, why carotene travels faster on the column? Why not beta chlorophyll? Molecular size? Yes? So see some animation. Imagine go back again. Back again. Okay. Look at the beginning of the race. Right? Click. All these sprinters are exactly on the same line. Do they remain exactly on the same line through the course of maybe 100 meters, 200 meters, whatever it is? No. Now why this girl reaches the goal first? Speed. She has the highest speed among the five. And this lazy girl, the last one. Right? So why is this separation taking place among the five during the running? Differences in speeds of running. Right? Now you answer. Why carotene comes out of the column first? Yes? Rate of migration of carotene is highest of the five, right? And that of the beta chlorophyll is the lowest. Next one. And therefore, if you see next, the migration velocity, we will call it, we will not call, we will call that not as speed, we will call that as migration velocity. So migration velocities of five solutes are different. Carotene having the highest migration velocity and beta chlorophyll having the lowest migration velocity among the five under given experimental conditions. Whatever column, the calcium carbonate slurry, ethanol, everything, conditions are same. Atmospheric pressure, temperature, right? Under the given experimental conditions, the migration velocity of carotene is the highest and that of beta chlorophyll is the least, and the three are intermediate between carotene and beta chlorophyll. So the separation has taken place because of the differences in the migration velocities of the 5 solutes when they travel across this column of calcium carbonate along with mobile phase. I have introduced the term mobile phase anyway. Next. And therefore, next. The 5 solutes are separated on the column because of the differences in their migration velocities, and migration velocities increase from beta chlorophyll to carotene. Now, hold on. Now my second question, that's fine, that carotene is traveling the fastest. Why? What makes carotene travel the fastest and beta chlorophyll travel the slowest? There has to be some reason, no? Why not beta chlorophyll traveling the fastest? Are you getting me? All the experimental conditions faced by these 5 solutes are same. No discrimination. And in spite of no discrimination, why is carotene traveling the fastest and beta chlorophyll the slowest? Molecular sizes he says sometimes, correct?
Absorption of this solute passing through the column because it absorbs the solvent.
Right. So, I normally give at this stage a hint that calcium carbonate is a good adsorbent. Right? Now, to some of you, there may be a question, what is adsorbent? And therefore, a few minutes on the phenomena of adsorption. Adsorption is a phenomena which is a surface phenomenon in which one solute called adsorbate concentrates on the surface of another solute called adsorbent. So it's just surface phenomena, concentration of adsorbate on the surface of an adsorbent. Naturally, this phenomena of adsorption depends on both the surface of adsorbent and also the qualities of the adsorbates. It will not depend only on the surface, it will not depend only on the qualities of the adsorbates. Let us see one example. You imagine, I always give this example, imagine this palm as a surface of an adsorbent. So this is adsorbent. You sprinkle water. Will it be adsorbed? It will be adsorbed. If it is adsorbed, try to use a tissue paper and try to remove it. Observation number 1. Once you wipe out, the surface is ready again, fresh. Same surface. You sprinkle some drops of oil, coconut oil, on this surface and try to wipe out. Which one is easy to be wiped out? Water, right? It means that surface remaining the same, the qualities or properties of two adsorbates, water and oil, were different, and therefore the extent of adsorption on the same surface of water and oil was different. That is called degree of adsorption, extent or degree of adsorption. Now, if we extend this analogy to the experiment of Mikhail Swait, what can we say? That these 5 solutes get separated because of the differences in their migration velocities, number 1, and that differences in the migration velocities is because of the differences in their degree of adsorption on the surface of calcium carbonate. Clear? Therefore, this is called as adsorption column chromatography, because the principle of separation is adsorption, right? It is being separated, and therefore in a column, therefore it is adsorption column chromatography. Now, your participation again. Instead of my palm as a surface, I sprinkle water on this surface. This is adsorbent now, table surface. Can you say with guarantee that water will be less adsorbed again on this new surface and oil will be more adsorbed? Can you say that with confidence? Answer is no. The reason is the surface has changed. Although the adsorbates are the same, the surface is changed. And therefore on a new surface you have to try. The new surface may offer the same degree of adsorption to these 2 solutes as the earlier surface. But it may not also. So let us assume now, and answer has to be very clear, and this box now opens. They are real shots, not real. Let us assume that in Mikhail Swait's experiment, all other conditions are kept the same, except that instead of slurry of calcium carbonate, we fill slurry of aluminum. Do you think that 5 solutes from chlorophyll will get separated? Number 1. If they get separated, will the sequence of separation be the same? I don't want quick answer, just think of it. First question first. What is changed now here? Adsorbent is changed. So surface is changed. So my question is, will the 5 solutes from chlorophyll get separated on this new surface? What will be your answer? What is I think? Maybe. Maybe. Why maybe is right? Because if this new surface, on this new surface, these 5 solutes have differences in the degree of adsorption, then they will separate. If they don't have, they will not separate. Now what about second question? Will the sequence of separation remain the same as in Mikhail Swait's experiment? Yes?
Depends on degree of adsorption of elevator.
Is it degree or
Rate of adsorption.
no? Still? No? No, एक minute. I'll give you. I'll give you. Why did 5 solutes in Mikhail Swait's experiment got separated? Accretion velocity is 1, but then their relative degrees of adsorptions were different, is it not? Relatively, carotene was least adsorbed, whereas methyl chlorophyll was most absorbed. degree. So for the sequence of separation, it may happen, I'm not sure, it may happen that beta chlorophyll will be least adsorbed, so it will come out first, and maybe carotene the last. So first question answer right is what he said is correct, that separation may take place if the 5 solutes from chlorophyll exhibit differences in the degree of adsorption on the new surface. Yes. And the sequence of separation will depend on their relative degrees of adsorption on this new surface. Agree? Sure? Another question. Now this time you have to be on the dot. I am not changing anything from Mikhail Sweat's experiment. Nothing at all. Everything, it remains as such, except that I don't put it on the column the mixture of, solution of chlorophyll, but I take 5 new solutes, A, B, C, D, E. I put on the column. And the same questions. Will these 5 solutes get separated on calcium carbonate slab? Because I have kept the surface same. Maybe. Maybe. Maybe you are one. Who else? Maybe you are? Yes?
Because they might have the same velocity or they might not have that.
No, we are not talking about velocity now. We are talking about degree of adsorption. So if these new solutes A, B, C, D, E, if these 5 new solutes exhibit differences in the degree of adsorption on the new surface, that is, on the same surface, calcium carbonate, then they will get separated. And what will be the sequence of separation? Depends. Now you are correct. Depends on their relative degrees of adsorption. It may be A, B, C, D, E, not necessarily in that sequence, or it could be anything depending on their relative degrees of adsorption on calcium carbonate slab. Right? Okay, close your eyes now. I will just brief whatever we have discussed so far. No cheating. थोड़े मेरा कहीं करना नहीं. Today's discussion we started with the experiment of separating 2 solid solutes, sand and salt, using water as a solvent. Separation took place because of the differences in the solubility of 2 solutes in a given solvent, water. Since the solubility differences are very large, separation could take place in one single step. On the other hand, if you have mixture of 2 solid solutes, one of which is completely soluble in water, another is partially soluble, then we have to resort to what we call as fractional crystallization. And fractional crystallization is a laborious, time-consuming process of separation. Similarly, when we have mixture of 2 liquids differing in their boiling points largely, their separation through distillation can take place in single state. But if their boiling points are very close, then we have to resort to fractional distillation, which is again a laborious and time-consuming process. Then we introduce the experiment of Mikhail Sweat, and we found that chlorophyll in fact is a mixture of 5 colored solutes: beta chlorophyll, alpha chlorophyll, xanthophyll, viola-xanthine and carotene. And this experiment proved that chlorophyll is a mixture of 5 solutes, but also it opened a new method of separation, which was coined as chromatography by Mikhail Sweat. And this chromatographic technique can be used for separation of colorless solutes also. Then we asked ourselves why the separation takes place. And then we said difference in the migration velocities. But why differences in migration velocities? Then we said because of the differences in their degree of adsorption. Carotene being least adsorbed travels fastest, beta chlorophyll the most adsorbed travels with the least migration velocity. And then we said that the phenomena of adsorption being a surface phenomena, and it depends on the quality of the surface and properties of adsorbate, that is solutes getting adsorbed on it. If a surface changes, we cannot predict that a particular mixture will get separated, and we cannot also predict the sequence of separation. The sequence of separation will depend on the relative degree of separation, relative degree of adsorption of these solutes on the given surface, and that these solutes will separate on a given surface only and only when they differ in their degree of adsorption. Correct? Concentrate झालं का तुमच्या डोक्यात? उघडा डोळ्यात. आतापर्यंत कळलं आहे का नाही? अरे तुला मराठी समजत नाही, तू कशी मान डोलवली? ठीक आहे. आता you just have to imagine few seconds, few minutes. Come on. That I am a magician. The great Dr. Sane, magician from GNRD, GN Khalsa College, Mumbai. Magician in a way that I take a glass column and I put a liquid in it, and I order that liquid not to flow out when I open the tap, and that obedient liquid doesn't come out. I have opened the tap. Magician, yes? Now what I do, I take a mixture of three solutes, A, B and C, put on the top of the column, and wash this column with another liquid which is immiscible with the liquid which is there in the column, glass column. And I see after some time A, B, C, they have separated. Now the first question is, why is there separation? The first answer is very simple, because they exhibit differences in their migration velocities. A is traveling the fastest, B the next, and C is the slowest. But why now? There is no adsorbent here, right? And still they get separated. Why? Yeah, I am adding a mobile phase which is immiscible with the liquid which is present, correct? So it passes through the liquid which is present in the column, and separation is occurring. Yeah, solubility, yes. Any other refined term can you use? Yes, you have talked. Solubility, yes. Because there are two liquids, my solutes can dissolve either in the mobile liquid or in the stationary liquid. Or they may have differences in the solubility in the stationary liquid which is in the column and the mobile liquid. This is called partitioning of a solute. Partitioning of a solute between two immiscible liquids. Give you a simple example. If you have done this experiment in physical chemistry lab, that is called determination of partition coefficient of iodine between water and carbon tetrachloride. Right? What do you do there? You take an aqueous solution of iodine. Is iodine soluble in water? By the way, iodine is not soluble in water. You have to add traces of potassium iodide so that iodine is converted into I minus. So K plus I 3 minus. And then this is soluble. So if you have aqueous solution of iodine in a separating funnel, you add equal volume of carbon tetrachloride and shake the funnel. Now carbon tetrachloride is a heavy liquid. So when you allow the two layers to separate, carbon tetrachloride is the lower layer, water is the upper layer. Now after you shake it for 10-15 minutes at room temperature, then even if you shake for another half hour, there is no change in the concentration of iodine in water and in carbon tetrachloride. It remains constant. Because iodine has already distributed. Iodine has already partitioned between these two mutually immiscible liquids depending on its solubility in water and carbon tetrachloride. So you can take out carbon tetrachloride and determine the concentration of iodine, and you can also determine concentration of iodine in water. Take the ratio, which is called separation factor, partition coefficient. So it means that every solute can distribute itself or partition itself between two immiscible liquids, and that distribution will depend on its relative solubility in the two liquids. This is called the process of partitioning. And therefore, this type of separation where solutes pass through two immiscible liquids and get distributed depending on their partition coefficient or depending on their solubilities in the simple language. This technique of separation is called as partition column chromatography, because the principle of separation is partition. It is being carried out in a column, and it's partition column chromatography. So we have adsorption column chromatography, and we also have partition column chromatography. At this point, before I break for a cup of tea, I will summarize and bring a very important point home. In fractional crystallization, separation could take place because of differences in the solubility of solutes in a given solvent. In distillation, separation could take place because of the differences in the boiling point of in a mixture. In adsorption column chromatography, separation could take place because of differences in the degree of adsorption of the solutes on a given surface of adsorbent. And in partition column chromatography, separation could take place because of the differences in the partitioning of solutes between two immiscible liquids. Now, can you tell me in all these four cases what is common? Differences. Correct? So, unless, please remember, unless solutes in a mixture exhibit differences with reference to some property, it could be solubility, boiling point, degree of adsorption, degree of partition. Unless solutes in a mixture exhibit some differences with reference to some property, they cannot be separated. Assume that all the 5 solutes in chlorophyll have the same degree of adsorption on surface of calcium carbonate, will you get 5 bands? How many bands you will get? 1. No separation, correct? And I always give some examples. Gitanjali, who? Amruta. Gitanjali and Amruta are fast friends. And I observe both of them always sitting together in front row, never separated. And one fine morning, I find Amruta sitting here and Gitanjali 3 rows behind, although the chair is vacant. Separation has occurred. Why? What could be the reason? Some fighting. She likes Tendulkar, likes Dhoni. To fight differences in opinion, who is the best? Separation. But then this differences in opinion is not very sharp. Next day they settle and then come back. But surprisingly, the next day, Amruta is sitting here and Gitanjali in the last row. Separation is very sharp and large. Huh? Why? What could be the reason? Any guess? It's not Tendulkar and Dhoni anymore. Any guess? This young handsome boy? Yes?
More differences, more problems.
Yeah, but what could be the difference? So sharp difference. It could be one handsome boy in the class. Is it not? We have talked about adsorption chromatography. Correct. Now, is calcium carbonate and alumina the only adsorbents available in chromatography? The answer is no. See, there are some basic qualities that adsorbents to be used in chromatography have to fulfill. For example, naturally, if you have 5 solutes from chlorophyll, imagine that they interacting with calcium carbonate itself. You will get something else, not the solute separation. So not only the adsorbents have to be chemically inert, but then they should not be soluble in solvents being used in chromatography. It's a very obvious thing. Next. Any adsorbent. Then, okay. Now, as far as possible, because there are exceptions to the rule, but as far as possible, they should be colorless. Like alumina is colorless. Then calcium carbonate is colorless. Magnesium hydroxide is colorless. Magnesium carbonate is colorless. But that is not an essential thing, because there are examples like, next, Fuller's earth, for example, or charcoal. Charcoal is dark and black. So in a way it can be called colorless because there is no color. Black is not a color. But then Fuller's earth and charcoal, they are very important adsorbents frequently used in adsorption chromatography. Next. Particle size. I mean, when I say slurry of calcium carbonate, what is the particle size of calcium carbonate when I make a powder? Normally we talk in terms of mesh. There are sieves, you will see in the laboratory, sieves, and 100 mesh sieves, 80 mesh sieves, 120 mesh sieves, etc. So normally in a column chromatography, we use 80 to 85 mesh particle size of adsorbents. Because if the particles are very, very small in size, let us take an example, that you have 80 mesh calcium carbonate filled in a column, and under atmospheric pressure, your ethanol is moving through the column at a migration velocity itself of 5 milliliters per minute. Correct? Now instead of 85 mesh, I still use a smaller particle size. Smaller. Will the migration velocity of ethyl alcohol increase or decrease? Will decrease, because this solvent will find it difficult now to move through the particles, smaller particles. It means that as the particle size decreases, the inside the column, the particles come closer, and therefore the mobile phase finds it difficult to move through. So the particle size is very important here. It should not be too big, it should not be too small. Too big, no separation, or very poor separation. If too small, then very slow separation, which is practically very difficult to manage. Next. See, we have two examples here. Large particles, and so this solute molecule moving through doesn't find it difficult to move through. Now the second column, particle size comparatively is small. Now, click on. Anyway, technical problem. So, out. Not as obedient as you are. Nevertheless, will it find easy to get out or difficult to get out? So that is the effect of size. As the size decreases, not only the solute molecules, but also the mobile phase will find it difficult, and the migration velocity will decrease with decrease in the particle size. Next. Okay, next. Go to the table. Click. Right. Now, generally, adsorbents are classified into three types: weak, moderate, and strong. Your question therefore will be, how do we classify them? So there is a very simple method. There is a set of dyes, colored dyes. Now I choose adsorbent A, put in the column, put the solution of dye and a mobile phase, and find out how long does it take for that dye to come out. And I do with a series of adsorbents. A weak adsorbent is one in which the dye comes out very fast, because degree of adsorption is very low. Like for example, sucrose and starch, they are not a good class of adsorbents. But alumina, charcoal and fuller's earth, the dye doesn't come out that easily, very difficult to come out. And therefore they are very strong adsorbents. And in between them are the calcium carbonate and calcium phosphate, calcium hydroxide and magnesium hydroxide, etc. So classification of adsorbents is based on the degree of adsorption of certain dyes, standard dyes, on their surface. Next. Next. Then go to 59. Yeah. I have not explained to you why I am not a magician. Earlier you have imagined that liquid remains stable, stationary in the column even if I open the tab. This is not a magic. What is normally done? Next. A fixed weight, let us say 100 grams of a stationary phase is taken. Normally, please remember in chromatography, in most of the cases, the stationary phase is nothing but silica, chemically treated silica of different particle sizes. So I take 100 grams of that in a round bottom flask, and then next I take a suitable liquid like a suitable adsorbent. I want a weak adsorbent or a moderate or a strong. Like that, there are different liquids. Some are polar, some are non-polar, some are semi-polar. So that suitable means that. So I take, let us say, 5 grams of that suitable liquid and dissolve that in minimum quantity of a solvent having low boiling point, like diethyl ether. And the round bottom flask is rotated, and on the top of the surface of this 100 grams, I go on pouring this suitable liquid. The solution is spread therefore uniformly on the surface of 100 grams of this solid support, which is silica. Next. One by one. This is round bottom flask, yes. This is Petri plate with silica particles of certain size, tube containing concentrated solution of suitable liquid in a volatile solvent. I put on the surface of this and then connect the flask to vacuum. What happens? The solvent is evaporated from the surface. What remains behind on the surface is a suitable liquid. I'll explain that again. Okay? Round bottom flask, silica particles which I take in the round bottom flask. Here is a solution, concentrated solution of a suitable liquid in a volatile solvent. Right? Now I pour uniformly this solution on the surface of solid support. And then I connect this flask to vacuum so that the volatile liquid goes out. What remains behind on the surface of support is 5 grams of suitable liquid coated on the surface of 100 grams of solid support. Now this physically coated liquid phase on the surface of silica particles, I fill in the column. So there is a liquid phase. Now if I open the tap, will it come out? Because it is physically coated there. And through this column, I pass another liquid which is immiscible with the liquid which is coated. And in this, the partitioning takes place, separation takes place. So there is no magic. Now since in this experiment, I have coated 5 grams of a suitable liquid on the surface of 100 grams of inert solid support, I will call this as 5% liquid phase loading. 5%. If I coat 10 grams on 100 gram surface, 10%. 1 gram, 1%. 20 grams per 100, 20%. Therefore, it is possible for me to make liquid stationary phases coated on the solid support of different liquid phase loading. Normally in chromatographic separation for practical purposes, the liquid phase loading ranges from 2% to 20%. Maximum is 20, not beyond 20 as a rule of thumb, not less than 2. Correct? Next. Okay, next. And therefore, once I do this, I have liquid phase ready for my partition chromatograph. Now, go back. Okay. Next. Go back. Go back. Huh? So we have now to take a revision. We have said fractional crystallization is used to separate solids from a mixture, taking advantage of the differences, next, of solidity, which we have said before the break. Next, in distillation, differences in boiling points. Next, differences in degrees of adsorption. Next, and then we have seen that compared to fractional crystallization and fractional distillation, chromatographic separations are simple and time-saving, less laborious also. Next, that for solutes to get separated, we have said, from a mixture, they must exhibit some differences with reference to some property, otherwise they will not be separated. Next. Next. Okay. Now there are some common terms used in chromatography world. We'll try to understand what are those common terms so that our further discussion becomes easy. Yes. A stationary phase, we have already used this word. Stationary phase which remains stationary, and this stationary phase could be either a solid or a liquid coated on the surface of the solid. Next, you have a mobile phase which moves across the stationary phase. So this mobile phase can either be a liquid or a gas. Can mobile phase be a solid? No. Solutes. We have introduced this term already, that instead of calling a molecule or an ion, substance, compound, we use uniformly solutes, and this is for all in all phases, liquid, solid and gaseous phases. Yes. Liquid phase loading is the amount of liquid coated for 100 grams of an inert solid substrate. Elution is the process of washing the column with a mobile phase, which can be either a liquid or a gas. Yes, here we have to spend some time. There are two important modes of separation in chromatography. One is called as normal phase mode of separation. Normal phase. Now please listen to me carefully. In normal phase mode of separation, the stationary phase is relatively more polar than the mobile phase. We are talking about relative polarities, not that one is polar and one is non-polar. No. I will repeat that when we refer to the term normal phase mode of separation, it means that the stationary phase being used is relatively more polar than the mobile phase. On the contrary, when we are talking about reverse phase mode of separation, the situation will be reverse. that the stationary phase will be relatively less polar compared to the mobile phase. And these are the two modes of separation in chromatography. 85 to 90% of the separations, you will be surprised, are carried out using reverse phase mode of separation. There are some reasons, and we will definitely understand them. And only hardly 10 to 15% separations are done by normal phase mode of separation. So you can imagine reverse phase of mode of separation in which the stationary phase is relatively less polar compared to the mobile phase is a method of choice. Next. Okay. Just one. Just concentrate on this table. I have put in the first column mobile phase, then the stationary phase, then the principle of separation, then the container or where the stationary phase is packed, and the common nomenclature. Very, very easy to know. Let us start from the first. Liquid phase, mobile phase is liquid, stationary phase is solid. As a rule of thumb, whenever stationary phase is a solid, the principle of separation is differential adsorption. Right? And when it is a stationary phase is filled in the column, the nomenclature is very simple. Start from the first column. Liquid, solid, adsorption, column, chromatography. Right? Nomenclature is very simple. Now the second, mobile phase is again liquid. Stationary phase is solid. So it has to be differential adsorption. So liquid, solid, adsorption. But here, the stationary phase is not filled in the column, but it is coated as a thin film on either a glass plate or aluminum surface, whatever. And therefore the nomenclature is very simple. Liquid, solid, adsorption, thin layer, chromatography. Then it is liquid, liquid. Liquid, liquid means partition. If that is in column, liquid, liquid, partition, column, chromatography. And if this partitioning material is a thin film, then it is liquid, liquid, partition, thin layer, chromatography. Now in mobile phase is a gas and stationary phase is liquid. Stationary phase liquid means partition. So gas, liquid, partition, column, chromatography. And when inside the column is a solid and gas, solid, adsorption, column, chromatography. Is there any difficulty in understanding this nomenclature? It's very simple. Remember only one thing, whenever the stationary phase is solid, principle of separation is adsorption, and if it is liquid, it is partition. If it is in the column, it is column chromatography. If it is thin layer, it is thin layer chromatography. Now why there is no mention of gas liquid or gas solid thin layer chromatography? Any answer to this question? Now, for example, for solid it is thin layer. For a liquid there is a thin layer. Why for the gas there is no thin layer chromatography? Yes? Gas cannot be what? Yeah, you want to say the right thing, but you are not finding the right words. So that is a part of effective oral communication. The gas in an open environment cannot be passed over as liquids over a thin layer under controlled condition. It will just go evaporate in the environment, right? And therefore, if somebody asks you, what about gas liquids in the gas solid? You say, no, it's cannot be, because gas cannot be controlled. Flow of gas is a mobile phase, cannot be controlled in an open environment. Right? Okay. Another question which is very frequently asked: what is the principle of thin layer chromatography? Come on. Now there will be 2 chocolates for this answer, not 1. Just think it logically. Table is in front of you. Table is in front of you. What is, if somebody asks you, what is the principle of thin layer chromatography?
Separation of pigments.
Sorry?
Separation of pigments on single layer.
No. Principle of separation. Just as we say adsorption is principle or partitioning is principle. What is the principle of separation in thin layer chromatography? Huh? Yes. But when? So you will have to ask question to the questioner. What is the stationary phase? If he says that in thin layer is made up of a solid, then the principle of separation of thin layer chromatography is liquid solid adsorption thin layer chromatography. But if it is a partitioning material, naturally it is going to be liquid solid, liquid partition thin layer chromatography. So there is no such thing as principle of thin layer chromatography separation. It all depends on what the stationary phase is made up of. It is solid, it is adsorption, partitioning material, it is partition. Very simple things, no? Many times we are stuck. And this, in spite of the fact that this table is in front of you. Okay, next. Now there are different chromatography techniques, and there are many ways of classification of chromatographic techniques. But I am giving one way which I find very simple to understand and remember. Yes. See, basically, broadly speaking, the chromatographic methods or techniques can be classified broadly into gas and liquid. Just hold on. A gas chromatography and liquid or solution chromatography are 2 broad classifications. Now, when can I call gas chromatography? When the mobile phase is a gas and the solutes being separated are also in the gaseous state. Because I cannot have liquid and still have gas chromatography. No. Under the given experimental conditions, the solutes being separated have to be also in gaseous state. Then I can call this as a gas chromatography. As against that, if mobile phase is a liquid and your solutes are in the liquid or solution form, then it is liquid chromatography. Now, we have seen here gas chromatography is further subdivided on the basis of the stationary phase. If stationary phase is a solid, we call gas solid chromatography. Or stationary phase is a coated liquid, then we call it gas liquid chromatography, GLC. Here it is GSC, it is GLC. And a very tricky question sometimes asked, whether GSC is gas chromatography or GLC is gas chromatography. You have to say that both are gas chromatography, in which mobile phase is gas and solutes are in the gaseous state under experimental conditions. Next. One here. Next. One more here. Yeah. Now go 1 by 1, okay? Liquid solution chromatography can be classified as already we have seen, yes, adsorption, okay, we have seen that, where the separation of solutes on the basis of their degree of adsorption on the surface of an adsorbent, yes. Partition we have seen, separation of solutes on the basis of their differences in partition coefficient into mutually immiscible liquids. Now you have one ion exchange. Here I would like to spend a minute or two. See, ion exchange is a process, right, in which there is exchange of similar ions between the ion exchanger and the solution in contact with it. If the exchange is of cations to cation, it is called cation exchange process. If it is anion to anion, it is anion exchange process. But when we talk about ion exchange chromatography, then there are two types. One is cation exchange chromatography and one is anion exchange chromatography. I'll give you examples. For example, if you have a mixture of sodium plus potassium plus iron plus 2, chromium plus 6, they are all cations, mixture of cations. And therefore, if your ion exchanger is cation exchanger, then under given experimental conditions of pH, solvent, etc., they can be separated. So it is called as cation exchange chromatography. Similarly, if you have mixture of chloride minus bromide minus iodide minus sulfate 2 minus phosphate 3 minus, mixture of anions. So you use an anion exchanger, and under suitable conditions you bring about separation of anions, mixture of anions. That is called as anion exchange chromatography. So ion exchange process and ion exchange chromatography. Large number of applications exist for ion exchange chromatography, and therefore it is one of very important techniques of chromatography. Then you have size exclusion chromatography. I think those who have done biotechnology will understand this size exclusion chromatography. Yeah? I will invite her here, please. I'm not doing anything, Baban. Please come and stand here. You also stand. Do you see? These are two molecules. Do you see difference in the sizes? There are differences in sizes. So in size exclusion chromatography, imagine that these two girls I put inside a column filled with a material having only fixed pore size, and that pore size is such that only she can go inside. What will happen to her? She will come out of the column. See? So she is still in the column. She is excluded. Now she has to also come out of the column. So I change the experimental condition and I flush her out, and she is separated. So in size exclusion chromatography, there is no adsorption, there is no partitioning. It is just physical changes, physical differences. Differences are to be there. So differences are in terms of size. So a column is filled with a material having fixed pore size. And if you have mixture of molecules of different molecular sizes, only those molecules which can go inside the pore will be retained by the column. The others will be excluded. The smaller particles will remain, smaller molecules will be retained, larger will be excluded. And therefore, this is used in polymer separation, in separation of proteins, and so many examples are there in biological sciences of size exclusion chromatography. Then electrophoretic. So there is a gel, okay, gel sprayed on a plate, and on one side of that you put a band of solutes which are charged in nature, and across the plate you apply electrical field. So there is anode, there is cathode. Now positively charged molecules or ions will move towards cathode and negatively towards anode. Now suppose there are 3 or 4 positively charged ions. One is carrying 1 charge, second is 2 charges, third is 3 charges, and the fourth is 4 charges. Right? Charges are different. So which one will move faster among these 4? Carrying 4 charges. Then the 3 charges, and then the 2 and the 1. So in electrophoretic chromatography, the medium used is a gel, and applied electrical field helps the charged molecules to move to the respective electrode, and the rate of migration depends on the charge. Larger the charge, faster the migration velocity. But you can also ask me a question, that we can have only 4 different singly or doubly or triply charged, then what happens? All of them are same charge, they contain the same charge. Then it depends on the size of the molecule. The smaller will move faster now, and the bigger, like me, will remain behind. So this is again a very important liquid chromatography technique, electrophoretic liquid chromatography. And the last one is affinity, which is so important in biological separations that you cannot separate otherwise in the absence of this. A very simple thing is done here. You know the antigen antibody reaction, right? Similar to that, the stationary phase field has on its surface certain structures, let us say locks. And you have different molecules, biological molecules passing through. Only those who can fit in the lock through affinity will remain on the column, the others will be driven out. And then you change the condition, change the affinity, so that which was retained also can be separated. So this is affinity column chromatography, extremely useful in separations in biological sciences. So these are the main techniques of liquid chromatography: adsorption, partition, ion exchange, size exclusion, electrophoretic, and affinity liquid chromatography. Next. Okay. Go to the figure. Next. Okay, column figure. Go to the column. Yes. So we changed the tracks slightly. So far we have understood the basics. Let us try to understand now with the help of this figure. A column filled with a stationary phase. 3 solutes being separated using certain mobile phase. Only thing, at the end of the column, I keep a detector or a sensor or a detector. Now what is the function of this detector, or what is the function of this sensor? The function is very simple. Whenever mobile phase enters into that detector or sensor, it remains quiet. It does not generate any signal whatsoever. But moment she enters into it, she will definitely, the detector will sense that Shubhangi or whatever and there are suppose 100 Shubhangis there, then there will be proportionate signal generated by this particular detector. So, the detector is specific to only solutes. As long as mobile phase is moving through that detector, no signal, but signal will be generated the moment any solute enters into it. And the amount of signal generated will depend on the number of molecules of that solute. There is a small, then the number of molecules is small. If it is twice, the signal will be twice, or thrice, or 10 times. Therefore, what will happen now? In this case, before A enters into the detector, there is some mobile phase. So mobile phase will first enter into the detector and no signal. Then enters molecules of solute A. Signal will be generated proportional to the number of molecules of solute A. After A is completely eluted, what is this there between A and B? Again, mobile phase. So mobile phase will enter, no signal. Molecules of B will enter, signal. Between B and C, mobile phase, no signal. C molecules will enter a signal proportional to the molecules of C, and after C there is only mobile phase. So the situation can be shown. Let us go to the graph instead of description. Yes, go ahead. Yes, please see here. One click. This is mobile phase moving through. Another click. So all the molecules are of the same color. So there is only one single solute. See there, as long as mobile phase is moving, there is no signal. Now, the 4 molecules enter the detector. See, there is a signal. Again, no signal. Next. See that, one click. Mobile phase. Next click. How many molecules are there now? 3. A, 2 molecules. B, 3 molecules. And C, 4 molecules. Next. Click. Okay. Now, for 3 molecules, you may get 3 pictures. A, B or C. Which one? Okay, show that previous one again. Okay, ask me again. Click. Yeah, click. Yes. See that again. Molecules A, how many molecules of solute A? 2. B and C. Go to the next one. So, out of these 3 pictures, which represent your mixture? Certainly, yes or no? B? Why? A, 2 molecules, B, 3, and C, 4 molecules. Whereas, in the first picture, it is 3, 2, 4, and here it is all RT. And therefore, what this graph signifies that not only it gives signal wherever solute molecules come out, but that signal is generally proportional to the concentration of the solutes coming out. Okay, next. We'll finish it. Go ahead. Next. Yeah, please click. Yeah. Next click. Same thing. Now we will have the form of simultaneous graph also. Yes, 2 molecules are recorded, 3 are recorded. Now 4 molecules are recorded. beyond 4 there is nothing, so no signal generated. Next one. So number of blue molecules 2, 3 and 4. Yes, next. Now, therefore, last point for today, if we plot a graph of detector response as a function of time, then the resulting graph, yes, click, detector response as a function of time, this is a different picture, not 2, 3, 4. But we plot a graph of detector response as a function of time, then next click. This is called a chromatogram. So if somebody asks you definition of chromatogram, then please remember I'm going to say that correctly. A chromatogram is a plot of detector response as a function of time in chromatographic separation. This addition that in chromatographic separation is important because detector response versus time, there are so many occasions when you can get the graphs. But when it becomes a chromatogram, when it is a plot of detector response as a function of time in chromatographic